All right, this is still section 1.1, and we want to look at solving systems. So their first example is our, let's see, so let me write down their example, 1.1.1. They want to solve 2x plus 3y equals 6. Well, there are a couple different ways I can do this. I can, and a lot of it has to do with equivalent equations. And an equivalent equation is one that has the same set of solutions. Okay? And, well, what we know is if I subtract the same thing from two sides of an equation, I get an equivalent equation. Okay? So if I do that, so let's subtract 3y from both sides of the equation. So these two equations are equivalent. They have the same set of solutions. And then if I simplify and write it this way, then this is still an equivalent equation. It still has the same set of solutions. And if I divide both sides by 2 by any non-zero constant, I will still get an equivalent equation. 6 minus 3y all divided by 2. So if I do that, so all these four equations are equivalent in that they all have the same set of x and y that solve them. And so I could write this as x equals 3 minus 3 halves y. That's also equivalent. And what we see here is that, well, x can be defined in terms of y, but y is arbitrary. Right? I can pick any y I want. Now, that's not the way we usually think of this up until this class, right? Normally, we would have solved for y, and so we could do that. So we could start with our 2x plus 3y equals 6. I could subtract 2x from both sides to get 3y equals 6 minus 2x, and I could divide both sides by 3 to get the equivalent equation of 2 minus 2/3 x. And again, here, x is now arbitrary. But then y comes from x. And we're very used to seeing this sort of thing for a straight line, right? But you see, x is arbitrary. So any time I change x, I do change y. But given an x value, y is fixed. Or up here, given a y value, x is fixed. Okay, so we've solved that system, and we see this is a case of infinitely many solutions, because I can pick x or y, one of the two, to be anything I want, and then that determines the other one. But I can pick that x or I can pick that y first, and I have an infinite number of possibilities to do for that. Okay, looking at example 1.12, now we have two equations, three unknowns, so x plus y plus z equals 1, and x minus y plus z equals 0. Now, here, they mention to get the solution, we're going to, so here's equation 1, here's equation 2, and what they want to do is they would like to take equation 1 minus equation 2 is the way they state it. Now, what are they really doing? Well, you could say that what they're doing is subtracting 0 from both sides of equation 1. So you see, they're kind of doing this. And this is why you get equivalent equations, is if I did this, I think everybody would say, yeah, obviously this equation here is equivalent to that one there. Now, even if that was a 2 or a 6 or whatever. Now, I'm using 0 because that's a 0. But if that's 0 and that equals is true, which it better be, then that's also 0. And so here, instead of using that 0, I'm using 0 written this way, x minus y plus z equals 1 minus 0. Okay, so there I subtracted 0, there I subtracted 0. I get equivalent equations. Now this is not the way I suggest you do that subtraction this way. That is very prone to error and it's just kind of messy and so forth. Instead, you have everything lined up. So there's x minus 1 plus z equals 0. And I would just do the subtraction this way. So minus all of that and minus that thing. Now, so x minus x is 0. Now be careful with negatives. Y minus, or minus here, a negative y, that's plus 2y. And then z minus z is 0. And then 1 minus a 0 is 1. And so we get 2y equals 1. And so y is a half, is one solution. And so that means that in this case, y needs to be 1/2. Okay, we've got that much of the solution. Now, if I plug that back in somewhere to either any of my equivalent equations, so for instance, if I take equation 2 and I say, well, you know, I have x minus y plus z is equal to 0, well, then that would say that x minus 1/2 plus z is equal to 0. And if I solve for x here, I get x equals 1/2 minus z. And in that case, well, what we have then is z is arbitrary. And so again, we have infinitely many solutions. Now, the way you might write this is, you know, something like x is equal to 1/2 minus, call it, we'll call it z bar, okay? Y is equal to 1/2, and z is equal to z bar, right? That's showing this z is arbitrary, okay? So that's arbitrary. So that's how I might write this solution. Now, I could also, I suppose, just implicitly write it as x equals 1/2 minus z, forget the z bar, and y equals 1/2, and not bother with this part down here. But I think it's a better, and it will help us out in the future if you kind of think of it that way with the z bar, you know, letting z be some arbitrary value of z bar, and then x is 1/2 minus z bar, if we think of it that way. Okay, so there are a couple solutions to these. We're going to get better at solving these things, more formal, or, well, more algorithmic in solving these. But for now, you know, that's just the idea. We're trying to get solutions to these systems of equations.